Quantum mechanic concept of probability. This is an electron. If you throw this electron at the barrier with the two slits, where on the back wall do you expect the electron will land? Let's throw this electron and see where it will land. That was not expected. Let's keep going. That was also not expected. But let's keep going. Right in the middle. Something unusual is going on here. Let's continue to throw a few more dozens of electron and then check in later to see what pattern appears on the back wall. A series of dark and bright fringes. How is this possible when there are only two slits that the electrons can go through? To answer this question, we will plot the intensity of these fringes on a graph and then use the quantum mechanical concept of probability to provide some insight to what is going on. In this graph, we will focus on the peaks, as these represents the intensities of the fringes. From here, we will switch over to the discussion of probability and then loop back after we have seen that probability also yields the same graph. This is the probability distribution of where the electron is likely to be found after the electron have passed through the barrier with the two slits. 16 of these probability distribution locations will be given unique ID names ranging from A to P. Using location H as an example, the electron has an equal chance of being in locations D, E, H, K, and L. This results in location H having a probability distribution of 5. This concept of the electron having the probability of being in multiple places will be applied to locations A through P. When done, the probability distribution for locations A through P now becomes familiar. Did you notice that only the diagonal locations were used? Take location H for example. This location is surrounded by locations B through M, but only locations D, E, H, K, and L were used, while locations B, G, I, and M were not used. This is partly due to probability, but is largely due to the wave property of the electron, and the concept in physics where a system tend to prefer situations with the lowest energy. Let's get back on track now. We have yet to determine the probability distribution for the two locations on either side of 3 in gray. These are 1. Utilization of neighboring locations does not apply to these two locations but instead is largely due to the wave property of the electron, and the electron's trajectory after it has passed through the barrier with the two slits. We will now add up the probability distributions within each of the 9 columns as seen in the row at the bottom. Next, we will compare each of the added columns to the middle column in blue, and then compute the decimal equivalent. We can now plot a graph using these decimal equivalences. Within this graph, we want to focus in on these 9 peaks. These peaks are equivalent to the peaks from the earlier graph of the fringes. Now that we have looped back around to the topic of the fringes, it is evident that the quantum mechanic concept of probability have been useful in explaining how we obtained the fringed patterns when we threw the series of individual electrons at the barrier with the two slits. Did you notice that in this simplified plot of the fringes, all of the valleys have values of 0? When a team of scientists performed the double-slit experiment using electrons in 2012, their graph have valleys that are closer to this. The valleys gradually increases toward the center of the graph. This gradual increase is again partly due to probability, but more significantly, it is due to the wave property of the electron. A more in-depth look at this gradual increase will be on a future video. Thank you for watching. I hope you've enjoyed this video and look forward to seeing you on the next video.